Okay, and let me share my screen. Hmm. Okay, can I stay in this mode? Can you read it, or do I need to go full screen?
I
Oh,
think full screen might be a bit better. Sorry, because I have half of my screen is split also to take notes.
how's that?
Perfect. Thank you.
Okay, so here's the only problem. I'm gonna have to count on Dave to stop me, is that now both of my screens are used by PowerPoint, so I don't see anything, including the chat or you. So you're gonna have to let me know if you have questions, speak up. I won't be able to see raised hands on the chat. Sounds good?
Yep.
Thank you. All right, so the Geoscience Paper of the Future was essentially an initiative back in 2015 of trying to get scientists to share their science so that other people could actually reuse or actually reproduce the content. And the basic idea here was to give a minimum set of requirements that wouldn't take a lot of time for researchers to actually do, but would actually improve our reproducibility problem. And this was actually done before FAIR existed, or FAIR was actually put together into a nice paper and advertised. And so essentially, it was really the beginning of that thinking. But it turns out that most of the principles from the geoscience paper of the future back in 2015 still apply today, with some changes which more have to do with better technologies for us to be able to share our science than the principle of it. So just quickly, again, this used to be a grant that was given to Yolanda Gill. She is a computer scientist at ISI, worked a lot with the geoscience community, and basically kind of got this whole like idea of how do I get to reproduce, what do I have to share to reproduce my science, got started. And I'll share this with you, but all the materials and all the slides, they're available through Leapfrogs, the platform. If you go to module 4, there is a link to it, and I can share the Zenodo link into the chat today or Slack. So why was that training done in the first place? In short, why do we want to learn to write a scientific paper of the future? And essentially, it had 8 goals. The first one is to practice open science and reproducible research. I think we've all taken a Science 101 class that says that science has to be reproducible to be science. And so the question is, how do we actually do this? The second is to get credit for all your research products. And so, for example, when you cite somebody's software, you want to give them credit for that software in the same way that you would give credit to a paper in your publications. You want to increase citations of your paper. And there's been some research done on this, that papers that have data and code and are more reproducible tend to be cited more often than papers that do not contain that information. Being able to write data management plans. So I don't know about other countries, but at least in the US, that's something that you actually have to do now for most funding agencies, where they want to know how and when and where you're going to share your data, your software, and your workflow. And to be honest, I took this course a little bit before I had to write my first grant, and being able to actually see the basic principle of it really helped me put that data management plan together. You can actually put all of your data and software citation into your CV. It's a product. It's something that actually counts. It shows that you're actually participating and producing something useful for the community. Helps you manage all of your research assets. So knowing what you've done, what you have, and what can be done can be very helpful when you're trying to write your next grant or you're trying to write your next paper to know exactly where things are. Be able to reproduce yourself. This is something that, when I was a PhD student, I was like, how can you forget your PhD? And now maybe with 15 years on my PhD, I can tell you, you can forget your PhD very easily. But the code that you produce during those years can actually be very useful. I still go back to some of my MATLAB code and try to reuse it. And unfortunately, I didn't do a very good job at keeping it in one place and also commented enough and reproducible enough that I can actually reuse it. But also funders and journals now require more and more that you have what's called an open science section that explains exactly how everything can be done and reproduced. So this morning session, essentially what we want to cover are general best practices on how to share reproducible workflows. What are the major concepts and goals? And it's really regardless of what language you're using, which platform you're using, which journal, which funding agencies. It's supposed to be really, really essentially broad, and it's meant to be this way to see essentially no matter what you do, no matter which field you're in, there is going to be some common things that you can do to make your science reproducible. And also the recommendations that are in the science paper of the future are mindful of your time. So the idea here is what can help somebody else reproduce your work without you spending, 20 hours putting everything together at the end of a project. What we'll not cover is things that are very specific to research areas. So for example, which metadata standard should I use for my remote sensing? We're not going to cover any software development skills. We're not really going to give you an extensive course on code sharing sites. We're going to cover GitHub. There are other things out there, but the principle that we're going to illustrate with GitHub are actually going to apply to the other code sharing sites. And also, we're not going to going to cover best practices in software documentation. So that's something we're actually going to cover in the third workshop on how to actually share your software. But as I mentioned before, for this workshop, it's not about like how good your documentation on your workflow and what it does is. It's more about making it essentially fair. So what I'm going to do in the next few hours, and we'll take breaks, essentially, why do we need open science? Go over this, and then look through the four different things that we need to cover essentially to make everything fair. So data, software, and workflows, mostly, and then talk about provenance and essentially saying, where does my software come from? How can I make sure that there is a good trace for it so that somebody can reproduce what I've done? And mostly we're going to be covering part 4 in this workshop. Data, as I said, a lot of it is field dependent. And so that's something that we can guide you a little bit in some, if you're in paleoclimate especially. Software is a little bit different from workflows, and some of you might be creating your own software packages in what you're doing, and that's fantastic. And this is going to cover a little bit about how to share your software, but really we're concentrating on how to share workflows here. So why do we need to share? First of all, because funding agencies are actually asking now for data to be shared and open. This is from the National Science Foundation and their public access plan now 2.0. But basically, they want to make sure that the research that you're producing with taxpayer money is open, immediate, and equitable access, essentially through their website. Publishers are also following this trend. So this is an example from AGU, the American Geophysical Union. And essentially now in their papers, they require an open science section that covers essentially mostly data and software. And what they're calling software actually covers workflows. And they give you some guidelines of what they want. And you'll see they're very, very close to what I'm going to show you today. And kind of leaves it a little bit up to you to decide how you want to do this and the how we're going to cover in the next 2 days. So this is Copernicus, which is another publishing a publisher. But basically what they're saying is that authors have to provide a statement on how their underlying research data can be accessed. And instead of something called open science, they call it data availability at the end of the manuscript, and they give some guidelines on how to do this. So it brings the question of what is reproducibility versus replicability. So in this workshop, and actually for all of frogs, we're looking at reproducibility. And really, we mean computational reproducibility, which means that you obtain consistent computational result using the same input data, the same computational steps, methods, code, and condition of analysis. So essentially, if I email you and you give me your data and you give me the code that you use to create your paper, I should be able to get the exact same result as you did. And that's always wanted. Like reproducibility is a bar, like the minimum bar in science that we want. We should always be able to reproduce each other's result. Replicability is a little bit different, and it has to do with whether or not you obtain consistent results across studies that aim at answering the same scientific question, but there is different ways of obtaining the data, the code, changing the method, and sometimes it involves new data collection or reviewing the data collection, using similar method, but not necessarily the same exact method. And if you don't replicate, it doesn't mean that something is wrong. Actually, that's like a lot of how science works, is that we change the data, we change the method a little bit, we get different results. That means something else for science, and we need to move forward with that. But again, for this, we're really going to be concentrating on that reproducibility idea. So the core recommendation that we make for scientific publication basically falls under those three different umbrella: open science, reproducible research, and digital scholarship. And I'm going to go over what it means exactly. And I should mention that a lot of this material is also coming from those different agencies/entities to actually create that idea of reproducibility in science. For the scientific paper of the future, essentially think about your traditional paper, the one that you read probably from a journal, which has a text that has the narrative of some method. So for example, it could say we run spectral analysis, and you're lucky if you get the method spectral analysis on our data. The data might be in some tables. We have gotten better at putting them into repositories, but it used to be tables in the paper, or it could just be figures, plot, nothing is mentioned. And, a lot of authors used to say, email me for the data, essentially. So when you want to write a scientific paper of the future, again, the first thing you want to do is thinking about how you make your research reproducible. So for software, it means everything from how did you prepare the data, how did you analyze the data, how are visualizing the data. And data preparation can be tricky because in some cases it can be very manual. You could actually say, we decided to remove this outlier. And that's from personal experience. We all do this, but for somebody else to reproduce your work, they have to also be able to reproduce that manual step. And then you actually have to be able to give provenance and the method that you're using. So the method could be just giving the script your code, but then it's not enough, right? You also have to say, okay, so what data goes in to the code? What should somebody reproducing my work, what should they expect coming out, both in terms of the file that's coming out, but also what does it mean? So something like, okay, if you put this data in, you're going to get a figure that shows an increase of parameter y over time x, for example. You also need to give information about what parameter you've used. And in some statistical code, and especially if you're doing machine learning, this matters a lot, what hyperparameter you're actually using, and also giving some information about how to run the code. So do you need, at the very least, do you need Windows, or does it need to be a Linux machine? What type of packages do you need? Things like this. So that's kind of the minimum bar for reproducible research. Open science means that, okay, now that you've prepared everything to make it reproducible, I have to make it shareable in a way that other people can find it, access it, and reuse it. So the sharing means you put your data, your software, and your workflows in publicly shared repositories. We're going to talk a lot about GitHub in this workshop, but there are other platforms. Use licenses that allow people to reuse your data and your software. Which license to use depends a little bit on your funding situation. So it depends, but as much as possible, it needs to be essentially open source. And also what metadata you're providing, and essentially giving a structured descriptions of how the data and the software is archived. So for data, I think we have a good idea of what it means to have metadata, at least have the variable names, have the units, have some information about location, things like this. For software, it means a little bit about, is it in Python? Is it in R? Is it in MATLAB? Is it a Jupyter notebook? Is it a series of .py file? What kind of license is associated with it, what kind of data can the software actually use, that it have to be CSV data, things like this. So basically giving that information to people. The last part to this is what's called digital scholarship and making sure that essentially every single component of your research products have persistence identifiers. So this could be a DOI. Actually, most of the time it's a DOI for software, data, and workflow, but also for people. And so I don't know if you're aware of ORCID or ORCID, which is basically an initiative to get authors identifier that are unique to them, so that if you change your name, the identifier stays.
Hey, Deborah.
Yes, Sam.
Sam has his hand up.
Um, Hi, Deborah. Thank you. I had a question. So I've seen these workflows in the past, and I've always been interested in knowing where do you specify how much compute you need to run this, and how do you make sure that that compute is reproducible? Because someone might have access to a supercomputer, and no matter what you do, you will never get access to that. So how do you make sure that that part is reproducible? And the other part that I wanted to ask was, you said open source licenses. Do you mean clear licenses, or do you mean open source as in it has to be completely open? Because there could be a CC by NC license, which means that it's a scientific product that's not meant for commercial use, but it's still open in the sense that it's utilizable by scientists, for example.
Yeah, so let me answer the second question first because it's going to be easier. CC BY is open; it's reusable by scientists. It might have actually not all CC BY have non-commercial. It has to be CC BY NC. And again, that has to do with your funding agencies, but actually having clear licenses that says how the software can be used is actually very useful for others to know what they can and cannot do with your software. Your funding agencies might have requirements on what they mean by open source, or some funding agencies actually says your software belongs to us and it's not open source. And so that's really going to come from your funding agency. If you do not have a mandate by your funding agencies, then the more what's called copyleft license you put on your software, usually the better. So I tend to be funded by NSF, which requires open source. So I tend to put licenses that only gives me essentially credit and force other people to reuse an open source license if they reuse my software. Does that make sense?
Yes, it does, but I will point out that you said copy left. Those are GNU and BSD licenses. MIT and Apache are not copy left licenses.
No, they're not. So that's why I said as much as possible.
Okay. Because most people don't, like, at least when they are working in companies, will not touch copyleft licenses, because the copyleft licenses requires the person using those data packages to then share it under the same license. So it's like a lot of people don't touch those licenses for obvious reasons. So there is that part, that balance between like, hey, do I want other people to utilize this and not be scared?
Yeah, and so that's the that's the line. I'll be honest with you. I tend to use Apache a lot, Apache 2.0, because it does have enough of a copyleft, I say enough, that other people can reuse it. It's open source, but it still gives me credit and people still have to reshare it under the same license. So somebody cannot take the work and basically package it for pure commercial use. Does that make sense?
Yeah, makes sense. Perfect. Thanks.
And then to your first question, can you remind me again?
Where do you report on compute resources? Because I feel like a lot of the times I've rarely seen that as like some people will say like this was run on this machine with this, but that does not mean that that makes it reproducible in any way because just because you ran it on a cluster with like an H100 GPU doesn't mean that everybody in the world will have access to it. So how is that still reproducible?
Yeah, so that's basically where those like gray lines happen. So in this case, if I had to use a supercomputer to run something first, here is what I would do. I would give, I would consider that a manual step. So as I mentioned before, in your manual step, you want to give as much details as possible that if somebody had access to that machine, they would be able to do it. And then have a warning essentially saying that you do need that compute. So where would I put this personally? If you're using Jupyter Notebook or if you're using a script, I would put it in those comments with a big like warning. I would put it in a README of my GitHub repository so that people actually are warned that it will require a lot of compute. If that is your final product, that's pretty much the only way you can share it. If it happens to be a intermediate product or you're doing science with it, then have the intermediate product somewhere and have the workflow that analyze the data available, fully reproducible within a container, especially if that code can be run on a regular computer. Does that answer your question?
Yes, it does. Thank you.
Well, I guess, can I say something?
Yeah, yeah.
I guess I got one similar situation to that one where you run a model and then a deep neural network on a really huge cluster, and then you want to make it reproducible. Of course, the people won't be able to get probably that large number of like GPUs, things like that. I think what you do is like you create a notebook where you share your training, process like workflow. And then if you are able to get one of those big machines, you will be able to run this. But otherwise, you also can share your weights. So you can just say, I don't know, let's say TensorFlow dot save your model, and then you also share your weights. So you can say, hey, let's suppose that you don't have enough I don't know, like machine for this, so you can just get the weights and then keep working like from there. I guess that could be one solution. Not sure if that could be totally reproducible, but at least you can give people somehow the way to start working from a one point, I don't know. I mean, that might be an idea, probably.
Yeah, and I think machine learning, or I should say deep learning at this point, is going to create issues that in a lot of other domain you wouldn't have in terms of computational dependencies and things like this. Because even sharing your weights, you still have to be able to reopen it on the same machine and so on and so forth, which is not that easy. But basically, the ultimate goal is, of course, you would want something that's fully containerized, fully reproducible. Somebody could just like press start and it would fully reproduce. That would be the dream. The reality is that you're going to always have edge cases. You're going to have cases like this where you just don't have the compute. And here is what can you do to reach that dream goal as much as possible, even if it actually at the end of the day means that pressing start is not going to do much because you don't have the computational resources. And so a lot of it has to do with if I had to do this again 10 years from now, what kind of information would I want to share with myself so that I could redo the work because I have access to that machine. And that would actually get you, it will get you a long way to actually help others reuse your work at the very least. Does that make sense? Yes?
Yep.
Yep,
Perfect.
it does.
All right. So again, what you want to do with data, software, and workflow is make them available in a public repository, even if it's not fully like computationally reproducible because you can't press start. But essentially, you want to give as much documentation as you can about your data, your software, and your workflow. Your workflow, which is basically describing what functions are being used, in what way, with which data and which parameters, is really what you want to document the most. And I would say there is two types of documentation. There is the computation part of the documentation, what a computer scientist would need, which is essentially what's the input, what's the output, what's the parameter. But there is also the scientific documentation as well. So telling people what they should expect, telling people how to interpret your results and what they should see in your workflow is something that you should actually also be doing. So that even if people don't get the exact same value, and that's going to be happening a lot, especially in data science type of applications, they actually get the right trend, they get the right information, and they can actually see if something is not right. So in terms of persistent identifier, so we'll show you how to get DOIs for at least your software and your workflow. For your data, it's going to be coming mostly from repositories that you're going to be depositing your data into. But you also need to get a unique identifier for yourself. And the best way right now is to use ORCID or ORCID to actually get that unique identifier for you. You can actually sign up on their website. A lot of journals now actually require that you give that ID when you actually submit a paper. And the reason has to do with if you change your name for XYZ reason, the work that you've done before stays attached to that number instead of that is persistent instead of your first or last name, which might not be persistent. So how does that compare to FAIR principle in terms of, you know, the guiding principle? So if you read the paper, essentially those FAIR guidelines were very broad, and a lot of it really had to do with not only what you as a researcher could do, but also what software repository, data repositories, people like running ORCID would have to do to make everything accessible. So FAIR is for everybody doing their part, whereas the scientific paper of the future really provides recommendation for your part, what you should do to basically help your community achieve FAIR science. And that's why we're not really teaching all of FAIR. We're only teaching you the portion that is the scientific paper of the future, where you actually get to follow recommendation that helps everybody. So a little bit about data. And again, I'm going to give you a generic example using a very broad repository. I'm going to actually say it from the get-go. I would not be using the repository myself for my science. You really want to go to a repository for your field and that accepts your data, but that repository happens to be a good example of what you should be looking for in terms of your community data-specific repository. And that is Figshare. If you've never heard of it, it basically allows you to share data sets, presentations, things like this in a way that allows you to make that data findable, accessible to other researchers, and at least reusable. And it gives you a lot of the information that you need, like DOI, citation, and so on. So Figshare is an example of it. I tend to use it mostly for presentations. So that presentation, for example, is on Figshare. I use it for posters. I use it for things like this that I want disseminated out there, and it's somewhere that is permanent and people have access to it without necessarily emailing me. But it's not like something where I have to give metadata that are very specific to my field, and I feel like people will need to actually be doing a lot of work to give me the right metadata to be able to reuse the data that I'm sharing. So data repositories, besides being very general or very non-general, you have things that are non-curated, so people can give kind of what they want. Zenodo, Figshare are example of those. So it kind of leaves it on the person doing the work to give the proper information. It's also not, well, curated, so it basically means that nobody is really looking at what you're doing and if you're doing it right, or if you're missing information, things like this. And then you have what's called curated data repositories, where essentially somebody is making sure that you're providing the right information for your work, and so on and so forth. Again, the two have different use. There is something now called the trust principles for digital repositories. So trust stands for transparency, responsibility, user focus, sustainability, and technology. And essentially, it really has to do with what data repository should be doing to make sure that the data is actually available and sustainable for all the community. So if you're looking for a specific repository because you don't know what you where to put your data, so usually if you're a graduate student, your advisor is probably going to tell you where to go and where to put it. But let's say now you want data from another community, and you're working essentially in a different field, then what you want to look is at a data registry, at a repository registry. And essentially what it does is register every single data repository out there. So one of them is called RE3 data. So if you type seismology, you end up with some of the data repository that contains seismology data. Another way to share your data is to actually write a data paper. So I think there is a few more since the slides have been put together. But the idea here of those data paper is I have great data. I want to share them with the community. I'm going to describe them as much as I can so that other people can reuse them in a bigger context. But usually what most of those data paper ask you not to do is to actually like interpret the data in any way or do science with them. So it's fantastic if you have essentially data that cannot really be, like you wouldn't be able to publish them by themselves, scientifically speaking, but you're putting them out there and you basically are getting credit for creating that data set. So the next part that you want to have your repository provide for you is some general and domain metadata. So again, if you're in a curated repository, usually they're going to guide you a little bit in terms of what metadata is needed. So general metadata are things like dataset name, the description of what the resource is, who created the resource, what's the publication date, what's the license, who I can contact, what's the version, what type of resource is it, where is it located. And again, the general metadata was really meant to be for every little thing that you can think of. So the general metadata could apply, for example, to a DVD on a shelf in a library. That's why location of the data matters. And it could apply to a data set living on a data repository somewhere. And that's basically something that's going to be shared across pretty much every single resource that you can think of. What's called domain-specific metadata is kind of what we think as metadata a little bit more, which is what standard was used to describe the data. So if you're working in geoscience, most likely it's going to ask you, for example, if it's coming from observation, where was that observation taken, like latitude, longitude, when was it taken, what are you actually measuring, what's the unit, things like this. And every single domain is going to have things that are more and more and more specific depending on what the intended audience and what the intended reuse is. So as far as choosing a license, so again, a lot of it is going to come from your agency. If you actually want to try to use something that helps you choose, Creative Commons has a chooser, a beta chooser that you can use, and it's going to ask you a multiple of questions like, can it be used commercially, things like this, and going to help you with their license. GitHub now is also maintaining its own, like, we can help you look for a license. It's not easy. It's one of the questions that I get the most, which one do you use? And honestly, that's something that I feel like AI could actually help us with in terms of choosing which license. The next part is you want your data to be accessible. And so accessibility, it's two ways. You can have what's called manual accessibility, which is kind of like shown here, which is click the download button and it's going to download the data. You could also have what's called an API, application programming interface, where you write a query to the data repository and it returns the data for you. And you can actually look at that documentation. The next step is to get a unique identifier for your data. So if you're using Figshare, it's actually going to mint the DOI for you, and you're going to have one. Your data repository, the one that you're using for your work, should tell you how to actually get that DOI. So DOI are not the only types of unique identifier that you can see out there. One of them is called a uniform resource locator, or URL. If you want to make it a little bit more persistent, you can use a Perl or a digital object identifier like a DOI. So URLs, essentially minimal effort to create. It's easy to create a web page and put data on it. The problem is that by its name indicate, it might not be persistent. So let's say you're a graduate student at a university, and as part of your PhD, you create a website and upload your data. It's going to have the name of your university.edu, probably saying that you're a graduate student, your name, and then the link to your data. The problem is when you graduate, your university is probably not going to let you keep your web page, and so you're going to be losing access to that data through that URL. So one way around it is to use a persistent URL, and essentially the idea here is you point to where the data was, and then you create essentially a pointer to where the data is at your great university. And it's going to give you a link that is always going to be the same. But let's say you move and you end up with another great university. You go back into that website and say, okay, now the data is at another great university, so point the Perl to it. And obviously, there are a lot of disadvantages here. The first is you have to move the data. So if you have very large data set, that's not really possible. And also, you need to not forget to update where that Perl is pointing to. Otherwise, basically, it defeats the purpose. So the best way is to essentially use a DOI, but they can only be issued by a DOI authority. So you do not have the right to create your own DOI. You have to go through essentially an authority that can do it, something like a journal. For data, many data repositories can issue DOIs for data. And also DOIs are always free. You shouldn't have to pay for getting a DOI for your data. So once you have the DOI, one of the things that you want actually say is how do you want people to cite your data? So Figshare happens to give you a citation that you can actually use. Other repository are going to ask you whether or not you want to how you might want to do it. So we work a lot with paleoclimate data and the NOAA. repository, NOAA allows you, for example, to use the paper in which the data appeared as the preferred citation. But essentially make sure that you tell people how you want your data to be cited. So why do you want to make sure people know how to cite your data? Again, it has to do with getting credit. And the more detailed research data you share, the more your paper is likely to be cited. So this is actually coming from a different field, medicine. But basically what they were showing is that when the data was publicly available, they received 85% more citation than when the data was not publicly available in their paper. And so that's basically why you actually want to make sure that data is there. Really has to do with people tend to cite papers that are more reproducible, ergo have at least the data in it more. In terms of what you want to see in your data citation, the author, when it was published, the persistent unique identifier, the repository, the name, but also the version. And what might happen is you might make some corrections to your data. You might want to decide to add data to it. Things can happen. And it's actually important for reproducibility that people have access to the different versions of the data. So for example, let's say that you created something, 5-10 years ago, and somebody wants to have to be able to see if the code will still work, or at least the method. It's important for them to have access to the original data to make sure that it's working. And even though the data is no longer, valid, or it shouldn't be used in science, or it shouldn't be because the corrections were important, it still allows you to validate code and validate some of the findings from before. So those are some of the what if situation that we actually get quite a lot. What if you have several data set in several file? Best practice is technically you create a DOI for each file, not very practical. So what you can do is actually put zip the file or put them in the same folder, put them on the same, for example, Figshare repository, and get one DOI for the entire set. If the data that you're using is from a public repository and you want to reuse it, this goes back to making science reproducible. You want to publish the query. What query did you actually use to get the data? So that if somebody, were to reproduce your work, they actually have access to that query. And then once you've done the query and you've massaged the data in any way, shape, or form, and by massaging, I mean like you literally have maybe like 3 different data frames that are coming out, and you just put them in one single data frame. So before any like data cleaning, any significant changes to the data, then you create essentially that combined data set and maybe create a DOI for it and get some metadata in so that people know where that data is coming from. If you get data from a colleague, it happens, usually people don't have the time. It's not like they don't want to share it publicly, it's that they don't have the time to do it and they don't know how to do it. So you could get permission from them to basically publish their data somewhere and giving them all the credit for it, but basically make it like go less dark essentially. If the data is coming from many sources, so it's not just one query to one repository, then you need to credit each source. And one way to actually do this, instead of doing it in a paper, is you put a table at the end that summarizes where each data is coming from. So Dave and I work in a field where individual investigators go out in the field, take a archive sample, make measurements, and that's one data set. And then we go in and actually try to take composites or do reconstruction. So some of our papers have hundreds essentially of those different data sets put together. So to make sure that everybody gets credit, creating a table like this is very useful. If the data is coming from a database, then go back to the data repository type of things, get the query and create one file for it and get a DOI for this one. And if you have many versions of the same data set, so either you create a DOI every single time that you change the version, or more and more, what you're going to see repositories do is that they're going to allow you to version under the same DOI. But then make sure that if you do this, you have the version of the dataset in your data citation. So what does it mean in practice for you? The first thing you want to do is identify a repository for your data. And again, depending on what your data product is, and again, your data product could be a poster, then you want to look at whether or not you need a general repository or domain-specific repository. Fill out the needed metadata. And again, don't forget the general metadata. I know it seems a little weird, like to think about dataset name and so on and so forth, but can be very useful for other people to reuse your work, especially people outside your field. If you're using a domain-specific curated repository, chances are you're going to be very well guided through all the steps on how to do this. And it might actually also tell you which license to use. Upload your data, get your persistent identifier and data citations from the repository, and actually cite yourself, which is the next part to this. That now a lot of journal requires you to essentially put your data in a data repository. You could still have an embargo, meaning that until the paper is published, it won't actually show you the data, but you'll get all of the metadata information and the DOI available to write your paper. And then what you do is you're literally citing yourself within your paper, citing the data and citing where it is, the repository, and so on and so forth. And the way you do this is essentially how you would cite any other paper. So in the text, when you reference your data, reference your data citation, put your data citation in your references. Some journals also require that you have an open science section or data resource section. So that's one way also to actually re-acknowledge your data in that section. And in some journal, they're going to ask that you put it in the acknowledgement section. But again, this is going to be journal dependent on where you put it. Putting it as an in-text pointer is not journal dependent, and that's something that you can always do, is basically give that citation to yourself. So let me take a break and see if there are any questions.
No.
No questions?
I have a question about your recommendation that you added zip your files. Do you recommend that even though we're trying to encourage people to be more cloud native and you can't read a zip directly?
Yeah, so I would recommend it for something like, we'll talk a little bit about this when we talk about workflows. If you do a sketch of the different workflows that you use, then I would recommend basically zipping them or putting them on the same Figshare repository. Like they're going to be PNGs essentially, or JPEGs, they're going to be images. So that I would recommend. Now, if you're talking about data that is going in and out of code, no, I don't recommend zipping, although you could technically unzip. So it's going to be dependent on your application.
Got it. Yeah, I was just thinking because you come across, examples like GeoParquet, on Zenodo, for example. You can directly use the HTTPS and do a direct read, versus if you zip it, then, someone has to download that and you can't really, like, it's not cloud native anymore, right? And there's some limitations there. So that's why I was curious as to like whether that was a broad recommendation or it's only for a specific, like, hey, these file types you have to download either way. There is no cloud native versions of these, so that's fine to zip. Versus, hey, these are the formats you shouldn't zip because they're designed to be read directly from those HTTPS links.
Yeah, and that's again like what I would say, it's going to depend on your repository and what you use and what you use it for. So if your repository says exactly this, you shouldn't be zipping because it's cloud native and so on and so forth, then don't do it. But I think, the problem is when we say data, we think about data, product of research, as in like for people who go out in the field, they make the measurements, they put their measurements maybe in a text or CSV or Excel or something like this. Or it's coming from model output. So you have a netcdf file, let's say, or I forgot the name of GeoTIFF, things like this. But there are other things that are data that are coming out of your research. So it could be a figure that's coming from your paper. It could be the workflow figure that I'll show you actually today. It could be a poster. It could be a series of posters. There is a lot more than just what comes out of a code as data. And so the recommendations here, they're supposed to be, broad enough to accommodate all of this. So would I zip, figures for a paper and put them together? Yes, that would be one use case where I use the zip.
Got
If
it.
I use something that's cloud native as a repository, then definitely not zipping.
Okay, no, that's good to know. I like that differentiated approach within the same output. Yeah,
Yeah, I think we forget a lot of what data is. Like we just think about,
definitely.
yeah.
Yeah.
All right, do you guys want to take a 10-minute break? Or do you want to power through software?
We got a couple thumbs up for breaks.
Yeah.
All right, let's take a 10-minute break. I'll stop the recording. Restart the recording. And can you see my screen?
Yep.
Yep.
Okay. Sorry, I was trying to get a third screen during the break so that I can have you on the other side. All right, so data, again, we're not going to cover as much because it is really data dependent. It's repository dependent. It is very dependent on what you're doing. Software has a little bit more things in common, regardless of what data you're using and how you should report it. So right now, we're going to concentrate on reporting the software, not executing it just yet. The execution part is coming on Thursday. So the question I'm also getting a lot is, what's the difference between software and workflow? And that's a very fine line. I'm going to give you my definition, and I don't even respect my own definition sometimes when I have to report. But to me, software is any functions, plural, that you will write that if you bring them together could form the basis for something that somebody wants to do in the future. So things that we can agree is more in the software category would be, for example, a diffusion model, like any type of models would fall under this. But also visualization. You could say, I really want to visualize that data this way all the time, regardless of what application I have. And so I'm going to create a small package to actually be doing that visualization. To me, that falls under software. Things that falls under workflow, again, in the workflow, you have the data that comes into it. So if you're starting to write a Jupyter notebook or an R Markdown, or you're basically saying to execute this Python file, you need to start with that data set. You're going to end up with this final product, which could be another data set, or it could be a visualization, or it could be a number telling you everything went right. That falls more into the workflow part to it. Now it's possible that, in the middle of your workflow, you're going to have functions to do things. And this is where maybe that doesn't necessarily fall under software. It's more still in the workflow part to it. So software here really is something that you plan to reuse for different applications, or something that you think people could find valuable. So the best example would be a model. So think about it in that sense for this part. So the availability of software, again, lots of journals now have requirements for you to basically be able to share what the software is. So here is where things are going to be a little weird, is that what a lot of those journals are calling software are actually workflows. But a lot of the principles are going to apply. But what they're saying is it should be published. It should be included in the paper on how to cite it, how to reuse it. It should be accessible for other people to reuse. And you actually, in this case, need to be a little bit careful about the license and the reuse. So for example, if you're using MATLAB, which needs a license to run, you're still able to share your .m files, but you cannot share the MATLAB computational environment for somebody to actually reproduce, like just click start and get the answers, because MATLAB is actually proprietary. So that's basically where the line is a little bit more than for data. So why do people not share their software? And it's little anecdote here. I was writing a proposal and we were actually asking people if they would be willing to contribute some of their software. And I literally got every single excuse that I listed here in the past 2 weeks from different people. But usually is no one would use my code if I shared it, which is not true. If you're going to give me code, I'm going to be very happy. That means I don't have to start from scratch. My code is really bad. Yes, so is mine. None of us are, perfect coders. None of us are computer scientists. And it's not necessarily really, 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 really bad. It's good enough. And anything you're going to provide is better than nothing. My code is not ready to be shared. That could actually mean a lot of different things, but usually it means it's somewhere on my computer. I'm not even sure if it still runs. I'm not really sure, how to share it with other people, things like this. Sharing my software will take a lot of time. It's true, if you're doing an entire documentation for the software and so on and so forth, it could take you a lot of time. However, if it has some documentation, at least if you're putting some comments in there, again, it's better than nothing. I won't get anything out of sharing my software. Not true. If you actually share it in a way that people can cite you, then you'll get citations. Have shared my software before and bad things happen. So bad things happen. The one that I did encounter this week was somebody tried to use it. They couldn't make it work and they kept emailing me to get help. And I became a software developer and helper. And it happens. So some licenses allows you to say as is, no warranty. And that's basically where it can be useful. You can also say, hey, I can't really help you. I work for the government, which basically means, I need to ask. I want to commercialize my software. And again, this is where the license could be important of how you can actually even reuse your own software. I don't want anyone to commercialize my software. That also has to do with license. And the excuse that we hear the most is, I don't know where to start. And that's basically what we're trying to address here is that last part. I don't know where to start. Everything else, there is a lot of truth to it. And, writing good code, writing good documentation is a skill. It takes time, but it's worth it. It's worth it for yourself as well down the line if you actually have good documentation for what you've done. So again, there is someone out there that will reuse your code. It is good enough. No matter what you're giving, it is good enough. Most people can read a Python script or an R script if they know the language and basically deal with it. But this was actually a joke from PhD Comics. I don't know if you still read it when you do your PhD, but the idea here is, anything would have been better than nothing to get this poor graduate student started. One thing that's almost also forgotten a lot is data preparation software dominates the time that you're going to actually spend in working with your data, but very few people actually share it. So, people are going to share, for example, their diffusion model or their hydrology model. but the code to get the data to that hydrology model somehow is not shared. That's the thing that is the most painful to do, that is the least reproducible, but people don't share it. And it is valuable. If you tell anybody, I'm going to give you code to help with, your data preparation, your data visualization, they're going to be very happy not to start from scratch. So in the same way that we have dark data, data that lives on somebody's computer, there is also a lot of dark software out there where the software is not published anywhere. And basically it lives on somebody's computer forever. And it doesn't actually get to be shared, doesn't get to be reused. And it's very true for data preparation and visualization software. So again, in the same way that we've talked about like different ways of sharing data, and that some things might apply to some data but not others, it's going to be very true of software as well. But when I mean software, I really mean everything. I don't just mean your model or your machine learning training. I mean everything that got you to the machine learning training, gets you out to the visualization and what you're actually sharing in your paper. So how do you make software ready for publication? And again, a lot of the concepts that we've talked about for data is actually going to apply for software, plus a couple of other things. What's the difference between the source code and what's executable? So basically making sure that you're sharing both, making your software run elsewhere. I have a Mac, and once in a while I have to remind myself that I'm only 50% of the population. The other 50% is using Windows, and that I need to make sure that my software is going to run on Windows as well. Make it modular. What that means is you don't want to necessarily write an entire function that does, the entire work. You might need to have a visualization function. You might have to have a data preparation function. You might have different data preparation functions for different data that are coming in, things like this. Make it configurable. Maybe have a config file, especially for models, where instead of actually having people write for each of the modules, how they basically write each module one at a time, maybe have a config file says, this is the module I want to use with these parameters, things like this. Something that is very useful even to you is learning how to write good error messages when something goes wrong. Because essentially most software, like most language that you're going to be using are going to have like basic errors, but in some cases it could be very simple. If you're actually writing software that is very specific to your project, it might only read one type of data and it might do it very, very well. But if somebody is trying to get a CSV file that's configured in a little bit different, it might not read it anymore because you weren't expecting that CSV. So having something that says, oh, wait, the CSV is this way, and then it's going to return an error is actually helpful. Provide test data. So, this is where computational expense can actually come in. But in some cases, it might be easy for you to provide very lightweight data to people to make sure that it actually runs. So an example of this would be, I have a large netcdf file or a large UTF. Can I actually grab only one data point or one grid point, sorry, and run that visualization on that grid point and put the grid point in a CSV, for example, so that everybody can have access to it. And also look at whether or not your code can be read by somebody else, and you can ask a friend. If you're publishing your software as part of a bigger workflow, I would say this is important, but not mission critical for your paper. If you're actually planning to create toolboxes for your community, then these principles are going to be highly relevant, and that's going to become more or less your life when you're putting those toolboxes out there. And, again, when I did my PhD, I was a chemist in a lab. I never imagined that I was going to be developing software for the paleoclimate community. So never say never. It might happen to you, but those principles will become really, really relevant if you get to that. So in terms of where to publish your software, we're going to use GitHub as an example. There are others out there. But essentially make sure it's in the shared repository that has version control. Version control is essential when you actually want to work with software for a couple of reasons. First of all, because you want to be able to see incremental changes as you go. But also if something goes wrong, and actually it's just say if, when something goes wrong, you want to be able to actually go back to a version that was working for you before. And so having something that has version control is very important. So to make it available, you can also do, if you really want to pass a small bar, publish on your website with a Perl at the very least. You can use a data repository like Zenodo and treat the code like data. A lot of people do this. They actually just put it on Zenodo directly, and at least it gets you a DOI. Again, the best is to use a code repository. It has other things that we're going to be talking about tomorrow in terms of helping you with collaborative effort. It actually allows you to track project development for your software. So it allows you to put goals on yourself, milestones, and actually tell people and yourself where you're going with this. And again, you can actually link that GitHub with Zenodo, for example, to get your DOI. And so there is a snapshot of your GitHub repository as you go on Zenodo once in a while. And we'll talk about how to link the both tomorrow, the two tomorrow. Another way of doing this, and this might happen if you have many users, is to create a community project, such as community projects that are created through Apache. And again, it's going to be very involved if you get to this, but if you have a lot of users and you get to a point where you can't address like, bugs in your code, if you have many users, then it's actually a good way to go. But what we do recommend is essentially using a code repository. It will give you the most for the time you're going to be spending, and it gives you additional things. If GitHub is too intimidating, you don't want to use it, then again, putting it into a repository like Zenodo or even Figshare would actually at least put it out there and put it out of the dark. So software repository, again, there's a little bit difference between the repository and the registry, same thing for data. The repository is where the code resides. It should support the evolution of the software, and it should support groups of developers. That's basically what you're looking for when you're looking for a repository. We're going to be talking about GitHub a lot. I think a lot of people use GitHub. There's things like GitLab and other Git out there that actually allows you to do this. A software registry is kind of the same thing as the data registry that was basically giving you information about data repository. A software registry gives you information about the software and where it lives and provides metadata. So software registry that you're probably very familiar with if you're using Python is Anaconda or PyPy, Python Package Index. If you're using R, Cran, forgot how you pronounce it. Siren, if you're using MATLAB, there is something called MATLAB Central where you can actually put your .m files. And there are other registries out there that you can actually look at. And again, at the bottom, I put Figshare and Zenodo. It's better than nothing in terms of actually putting your code out there and for people to be able to reuse it. So the second thing that you actually want to give in terms of your software is actually metadata about it. So a long time ago, somebody I work with basically created guidelines on what computer scientists think about what should be in software metadata. So I'm going to run through it a little bit. And what they did is essentially have a software registry that would walk you through those 6 quadrants and ask you a question about it. And as you were filling it out, it would turn green. And it turns out that people really want it to be green. And so people were giving more and more metadata. But the reality is you probably will be able to give some of the information. So identifying the software, what's the name of the software, the description, so essentially what it does, what's the unique identifier for it, so the DOI that you get, What is the general categories for your software? So is it, for example, a model? Is it visualization? A general category could also be Python versus R versus MATLAB, things like this. And also, if you have any project website, the repository, some documentation about the software, that's where you would actually put it. The understanding, again, it has that idea of general metadata. It would apply to any software out there versus domain metadata. So things like who created it, who contributed to the software, who published it, who funded the software, some statistics about the software, ratings, like 1 to 5 type of things, or any publications, project using it. Some information about running, for example, and support. Like if I need help with the software, where do I go? And it could be also as is, there is no support. Then you might have something like domain metadata. So software that could be used with your software in combination to work with some application. You could actually create that kind of link to your own software. So you could, for example, have a software that does your hydrology model, and then have software for data preparation, software for visualization. And so you could actually say, hey, if you're going to use my hydrology model, here is a link to the software that allows you to do a lot of the data preparation. Here is a link to the software that allows you to do a lot of the visualization. What are the recommended uses and assumptions that are being made when using the software? Constraints on its use with data. So, for example, things like it will only take data in that particular format. And what's meant by format here is a little bit more than just .csv. It could be it's a .csv with the first 5 lines being metadata, the 6th line being the headers, and then the data itself. And that really allows you to code because like around it very efficiently because you know where things are. But it could also be constraints like we've talked about before, like what type of computational resources do you need to actually run it? So if it's a deep learning model that has many, many neurons, you're going to probably need GPU type resources, so you could put that here. And then some domain-specific keywords. So if you're using, paleoclimate as your general keyword, it could actually say it's for time series analysis, or it's for calibration of X. If you're using it for remote sensing, you could have remote sensing as your general metadata and have something very specific about what type of remote sensing you're doing with that software. The next part is executing. So basically the license, where is the code? If you can actually execute it somewhere else, where could you execute it? Information about how to install it. And so basically anything that has to do with documentation of your functions. So if you actually ever use somebody else's software, there is usually a documentation that tells you this is the input, this is the output, shows you a minimum example on how to use it. Installation instruction, what's the implementation language? What dependencies do you need? And what are their version for Python? That's usually something that's very important. What type of memory requirements are needed to run your software? What is the OS requirements? What's the average runtime? And other details. Can it be implemented in parallel? Things like this. So again, really, the dream here is to be able to have somebody press start and it would run, but that might not be possible because of computational resources. So the more information you give in that metadata in terms of what's needed for somebody to run it, the better. And then if people are interested in using it and running it, it's always a good idea to have some testing instruction. So if you're using something like Python, you can use something called PyTest that people can run, and it says if it passes the test, it actually it tells you that you have it installed properly and it's working properly. You can also give some test data set for like ship it with the package so that people can actually try it out and see if it's running properly. Tell people how they can get support. So it could be how do you send question or report bugs about the software. So one of the way to do this, we'll talk about it tomorrow, is using something called GitHub issues. When somebody has an issue with it, they open an issue and somebody fixes it. and what type of support is provided. And some people are going to tell you as is. So basically, they don't want to provide support. You can use as you want, but basically, you're responsible for fixing the bugs, or you need to find somebody to help you fix the bugs. The next part to it is actually explaining how you can use your software to do research for scientists. So at the end of the day, we just don't want to play with software. We actually want to get science out of this. So basically, what type of input and output data are there? What type of parameters? What do the parameters do? And also like link to relevant data sources that people can use with the software. So it's a little bit different than just providing a test data set. This is really telling, hey, you can use my software with data that is contained completely on this database or this other database, but it's more than just a test data. Composing essentially with that software. So what is it interoperable with? So fair, I is interoperable, right? So if the output of your software is not in a format that anything can read, it makes it very unuseful, right? So basically, you could have something that writes a hydrology model. At the end of the day, you get a netcdf file. The netcdf file can be read with this library, and you can actually explain to people this is how you would actually read the file and work with the data. And then how to cite. So again, like we did with data, what's the preferred citation for the software? So it could be as a project, it could be because it was described in a publication, or it could be from a DOI. How is it updated? So basically something that you always want to do with software is track the version. It's actually almost as important, if not more important, than data, because software evolves over time. And so if somebody, wrote a paper 5 years ago with version 1 of the software, it might be very different than version 2 of the software. And that could have to do with the fact that you can have a default parameter value that has changed between version 1 and 2. And that's going to affect essentially your results quite a bit. So when you're reproducing somebody else's data study first, make sure that you have the right version of the software. When you publish your own, make sure that you tell people this is the version of the software that I use to actually create the results that I have in my paper. And also you want to tell people how to contribute. A lot of things that are open have open communities around them. And so the idea here is to get contributors to help you with your software, develop with you. And in that case, you need to actually tell them when you're planning to do releases, what are the milestones that needs to be reached, and things like this. You might be called upon at some point helping somebody with our software because they have everything you need except for one function. And it might be better for you to write that function in their package rather than rewrite the entire package for that function, right? So that might actually happen on both sides, where you want to contribute and you need to have those guidelines, or you want other people to contribute and you need to give them guidelines. So many software repositories that you're going to be using, like GitHub, actually do capture some of that information automatically. So for example, GitHub capture contributors automatically. You don't have to actually keep track of this. But some of it you're going to have to do manually, especially when it gets more into your domain and more into your specific application. So the next thing that you want to make sure that your repository has is how to access the code. So on GitHub, if you click on this, it tells you how you can get the code out. So at the very least, in this case, you can actually download the code on your computer directly and use it. You can actually create a copy and still contribute to Git. Many options. In software registries, it's actually going to tell you the same kind of information. At the very least, it's going to tell you how to download the files that are relevant for the software. And hopefully somebody put a README in those files and tells you how to install it. Or software registries like PyPy, you can actually directly install from that registry by doing pip install or conda install. depending on which one you're using in Python. And I haven't used R in 10 years, so I'm not really sure how you do this in R, but I think it has something to do with install as well. You want to chime in here, Dave?
Yeah. Mostly in R, we just use the function install.packages. It's automated that's going to come from CRAN unless you specify a different repository. A lot of us use packages from GitHub as well, which you can use remotes, the package remotes to install from GitHub. I'm going to talk with the R folks about the RENV package, which will help you with your package management and making sure that your end product is reproducible with the same packages and versions.
Okay, so the next step is to get a unique persistent identifier. And unfortunately, GitHub doesn't do this for you automatically. You cannot get a DUI from GitHub directly. So what most people do is that they link to Zenodo. And so every time you do something called a release is essentially a snapshot of what your repository looked like on that day. And then it actually saves it on Zenodo with a new version. That's how you version your software over time, essentially, by taking those snapshots, putting them on Zenodo, and you can get a DOI. And again, the DOI, you have two types of DOIs on Zenodo. You have the DOI that works for every single version. And then you have a DOI that's being minted every single time you release a version. So you can either cite the specific DOI of your version, and then people should be able to link back to the version, or you can cite the like umbrella DOI, for lack of a better word, and then say, but I was using version, I don't know, 0.14.0 of the software. The next step is to, again, tell people how you want them to cite your software. So again, it could be coming from a paper, not the preferred method for software, because your paper could be 4 years old and version 1.0 of the software, and you could be at version 2.0. And so what GitHub allows you to do is create essentially this file called citation.cff that gives the information about who wrote the software, the title, the version, the DOI. And if you click on this little arrow, it would actually give you the citation in BibTeX and APA format. So that's actually one way to get a citation for your software. And it turns out that there is a link to Zenodo too. So if you update that citation file, the citation will actually transfer over to Zenodo as well. So you're only doing it in one place. So how do you implement those recommendations in practice? Again, identify a repository for your software, preferably one that tracks changes over time and allow for version releases. For this course, we're going to teach you GitHub because it is widely used. Just know that some domain have their own repositories for their software that has that version control and so on and so forth that you can also use, but that's going to be more dependent on your field. Fill out needed metadata, and either you're going to be guided through some of these steps if you're using a software registry, or you might actually have to do it manually and think about what should be in it. Upload the software and get your persistent identifier. With GitHub, you would have to do this with Zenodo. How to cite? Now, same thing as data or actually papers. So now that you have a citation for your software, you can use it as an index pointer as you would any other paper. You might have to put it in the data resources in the acknowledgement section, depending on the journal. And again, like it's kind of those things, read the instruction for every single journal. But more and more, you'll see it as an index. Like, as you say, we use the X software, and then you cite the software. All right, so that was software. Now, methods and workflows. So again, the line here is a little blurry, and I'm going to acknowledge that from the get-go. But think about workflows more as how you use the data in the software to do your science. So if you write a Jupyter notebook, an R Markdown file, and I forgot what it's called in MATLAB, and you say, I'm going to use this data and we're going to write this little line that calls the software, and then I'm going to get those results. That's where you're getting into that workflow part to it. So why does that matter? Usually what was done before is that the methods, the workflow really, that was described in text was often very incomplete. And essentially, there are more papers out there, but really it started in 2009 where people looked really into reproducibility and how to achieve it. And they turned out that in most cases, they could not reproduce the study even though they had access to the data. And the reason is because if you say something as general as I ran, I don't know, a deep neural network using a CNN on my data, it's not enough information. At least I need to know how many layers, I need to know the hyperparameters, I need to know what the split in the training and testing was, and so on and so forth. And it turns out that the more advanced the method, the worse the problem has become. The more recent paper that I read on this was actually from last year, where they actually looked at computer science, machine learning papers, and gave themselves 40 hours to try to reproduce them. And what they found is essentially the only way to achieve mostly reproducibility was if the data, the code, and the workflow was available to them. If you were missing any of those things, it was almost impossible to do it. The second problem of not just being missing is that it's also ambiguous. And so if you leave it to people to figure out and fill in the blank, they're not actually going to necessarily fill in the blank properly, right? And that has to do with the fact that English is ambiguous as a language, or any natural languages are actually ambiguous compared to computer code. And so if I tell you to, I'll give you a simple example, to run spectral analysis on that data set, well, we all understand what spectral analysis is, but there are many methods to do it, and there is many implementation of those methods, and sometimes that can actually play a role in not being reproducible. So basically, the least you leave it to people to interpret what you've said, the less error you're going to get in your reproducibility. And really, the only way to do this is basically by describing to somebody, this is the data that I took, this is the code that I run with that data, and this is what I got. And that basically sequence, and actually I should say that complete sequence of I took the intermediate output and kept running, is essentially what's called a workflow. So workflow is essentially a common term that we all use to denote any organized activities. So you could have workflows in life. So for example, if you go to the hospital, you're going to go to the front desk, they're going to admit you, they're going to ask you a series of questions, including your insurance information. And then the next step in this is to make you wait and find which doctor you can actually see, have the doctor come, and so on and so forth, right? So we operate through workflows pretty much in our daily lives. So in terms of what we're talking about this week, we're really talking about computational workflows, which is basically something that's composed of programs. So an example on the right-hand side in paleoclimate is to create a temperature composite. And if you read this, even if you're not in the field, what you should understand that there is an input of something called PDB that goes into a program called transform, has an output, then I remove the duplicates, and then I need a series of other steps, right? But basically, as a human being, you can follow the information and follow through the step to see which data went in, what data came out, how that output was used in the next function. And even though you might not understand all the method, you might not able to understand everything that's going on, you can actually still follow what's happening through the entire process. And that's basically what's called a workflow. So the idea of workflows is you represent the computational step in such a way that other researchers can visualize the data flow through your work, but it's black box enough that it doesn't actually describe in great detail. Like you're not basically drawn out into the details that only maybe somebody in your field could understand. So usually when you do workflows, what you want to show is the data flow through the software, but most importantly, you want to say what parameters are important and what the value of those parameters are. So I teach data science, so this is coming from a data science class, but it was basically looking at the example of writing a cipher. So I think in this case, it was a Caesar cipher. And so what Caesar ciphers do is that they take a sentence or a word, and for each letter, they shift into the alphabet by a shift key to basically scramble the text. It's the simplest cipher that exists. But here you get the idea of, I took a document, I shifted by a certain number of space, and I get an encrypted document, even if you don't know the actual details that goes into the cipher function. That's basically what workflows do. They allow you to say, okay, now I have that software, I have that data, I can try to reproduce the work. So what you do with computational workflows is that they only contains the computational steps. So in this case, it would be, I want to run the spectral analysis, or I want to run my cipher, or I want to run my temperature, composite, things like this. However, in scientific workflows, you also have manual steps that actually you need to be able to capture and describe. So it could be something like cleaning data in a spreadsheet. And so you might want to say, we looked at the spreadsheet and for, that we removed that data point for reason X, Y, or Z. But it could be something, as we've talked before, where, well, we did some data preparation, but it's too big to do that data preparation on your machine. And so I'm going to describe what I did, but I can't actually give you the code for it. Or even if I give you the code, you won't be able to run it because you don't have the computational power. And so you need to capture this somehow. And so this is why people use drawings to actually show where things are going, where the manual steps are, where the your notebook be coming in, things like this. Your workflow also need to include the steps that you use to access some web services. So for example, looking up a data set in a database. So hopefully you have a database that has an API. There is an actual query. You can actually share that query and it's a code. But in some cases, you might actually do a manual search on the database. And so you might have to write, I went into the text box and search for X. Nowadays, we work with LLMs. And so things are getting even more complicated if you're using an LLM to do anything, which is you would actually have to give the actual prompt, because it turns out that you're going to get very different answers from ChatGPT depending on how you ask the question. So things like this that really allows for reproducibility as much as you can. So the level of details that you want to give depends a little bit on your audience, and it depends on what you're trying to achieve. So you can think about it as two different ways, which is the abstract way of thinking about it. And so if you read the one on the left, it tells you, I'm going to remove my outliers, I'm going to hypothesize over missing value, I'm going to run spectral analysis, and I'm going to run a significance test. Everybody can understand this. I mean, with some statistics background, but basically it doesn't give you a lot of information, but it gives you a good flavor of what you're trying to achieve and what was achieved. And that's great for a paper that is read by a wider audience. Now, you can also give the algorithmic method where instead of just saying hypothesize over missing value, you said we use linear interpolation, we use this very specific spectral analysis method, and we use this very specific significance testing. And that's very useful to go in your GitHub repository or to go into your notebook for people to know, okay, that's the exact method that you used. Now I can actually really follow what you're doing in reproducing. Both are valid, both are useful, and they're used basically for different audience and different things that you want to report on. So The workflows that I've shown you until now, they're actually coming from a workflow system called Wings. Not all of us use workflow systems. Actually, most of us don't. And so what you can do is essentially sketch them by hand. The advantage of sketching them by hand too is you can actually capture those manual steps somewhere, and you can give some descriptions of those manual steps. But it basically works the same, where you basically compile all the code that you've used. So it could be a .py, it could be a function, it could be whatever you think is appropriate, essentially. Compile the data that are being used by the function and being output by the function. And essentially show people with arrows how the data flows from one thing to the other. And so you can do this with PowerPoint. Most people, like I found myself that now I use them to actually describe my own work before I actually start it, so that I know where I'm going with things. But they're actually useful, and it's a useful way of visualizing where things actually go and are. You can use different colors, different shapes and so on to describe different things. Usually one of the things you want to do is have different shapes for data versus software. You might want to use different colors to represent manual steps versus things that are computational. Some people use it to describe software that's data preparation versus analysis versus visualization. That's kind of up to you. Just make sure that you actually give a legend in this case. So again, the advantages for sketching your workflows, it will help other people essentially reproduce what you've done, because you're showing them a sequence of the steps and what the expected output are and what parameter values you've been using. It allows you to communicate more effectively what you've done to your peers and to your advisor. Turns out if you actually put this on a slide, your advisor might actually understand what you've done a lot better. And it actually might help you as well to plan your own analysis, to see where things are going, things like this, and what you're missing. Like sometimes just sketching it, you realize, oh, but I need that pre-processing as well. And you can always go back and edit. So it's, again, this is not something that most of you will see, but just so you know, there are workflow systems out there that actually allows you to get the method as computational workflows. You can actually, in that case, press start and it will rerun it for you. It might also help you to do some validation work. We actually will talk about some workflows when we'll talk about GitHub Action. That's one of the one that you're going to be using. It allows you to scale your computation. So some system like Pegasus, what they're meant to do is take bits of your computation and actually send them on different machines so that you can run faster. And it allows you also to work across multiple programming languages. So for example, you have, I don't know, your model in R, but you want to do your analysis in Python. Those systems really allow you to have the two communicate a little bit better. And each system is going to be different with different capabilities. So depending on what you need, you might use different ones. So we're going to talk about GitHub and GitHub Actions. Another one that if you're interested in scaling up your workflows, I would look into Apache Airflow. In terms of workflows and how you do it, from the sketch to the execution. So one way is to use what's called electronic notebooks. So the most famous out there for Python is the Jupyter notebook. I'm sure a lot of you are familiar with those, so I'm going to go a little bit faster. But the idea here is either one cell represent one step in your workflow, and that might be hard, or you can do one section is representing one step. So essentially, each one of those boxes with the data coming in and out is one step in your computation. And what you want to do is say to people, you use this data with the cells below, you're going to get the following output. And again, because we're doing science, it's always a good idea if you have a figure to tell people, this is what you would expect the figure to look like, so that they can actually reproduce. The advantage of using notebooks is that the explanation that you're putting in text stays with the code and the visualization. And so everything stays together. Another advantage that I didn't put here is that if you have a manual step, you can still create a section here and have the manual step described into the notebook. so that people can actually redo your manual step. So Jupyter Notebook for Python, actually Jupyter stands for Julia, Python, and R. So technically you can do all three in there. R has something also called R Markdown that Dave will go over tomorrow. If you're using MATLAB, it's called the MATLAB Live Editor. I've never used it, but it's basically kind of the same idea of having the explanation stay with the code. And there are many advantages to using Notebook. You have an interactive computing environment, and there is a way for you to share your notebook with its computation environment so that people can actually play with your notebook. It allows you for interactive data visualization. The visualizations stay with the code, so you can actually comment on it. It does a great job at documenting the scientific process and not just the functions. Actually, why and what it was found and why you think it's correct. There are many tools for collaboration out there. So an example is Google Colab. It basically kind of works like a Google Doc document that you can actually collaborate on. You can easily share them. You can convert it to a PDF if you need to. And it allows you to compile all aspects of your workflow in one place. So again, if you have manual steps, it allows you to have some text about your manual steps in there, which will help people with reproducibility. As Dave mentioned, that's not the only way. What you could do also is have a series.py file or .r file, and then tell people literally in text in a README, you use this data, you run this .py, you will get this, and so on and so forth, so that people can actually reproduce, or you can make that easy little drawing on the side that shows how to use the .py file. So things to keep in mind, regardless of how you do it, either you use a notebook for everything or you use a README and a drawing to show which file to use. You need to make sure that another researcher can actually reuse your computing environment. So you might have to tell which version of the language you're using. What are the hardware dependencies? Especially if you're doing deep learning, you're going to get into CUDA and NVIDIA very quickly. And so you actually need to have that information. What are the libraries that were used and their associated version? And we'll talk a little bit about this on Thursday, about environment files and how to create them. And again, the version is critical if you're using default parameter values, because those might change over time with different versions of the software. And so you want to make sure that people have access to actually the right parameter value. And again, the manual steps needs to be there somewhere for reproducibility. So a better way, instead of putting this in a text, in a README, is if you can, is to share the computing environment and have it basically execute somewhere else. So in terms of sharing computing environment, what we mean is the code is the artifact that needs to be executed. So it could be myscript.py, myscript.r, myscript.ipynb. The code repository is where your code lives, hopefully with version control like GitHub. The computational environment is the dependencies that you need to run your code, and the computational infrastructure is where your code needs to execute. So things like, I need a Unix OS with 10 gigabytes of space minimum and 2 GPUs. And it might get more complicated saying exactly what GPU type you need and so on and so forth. And that needs to get somewhere into your README, or even better, at the top of your notebook. You can also share virtual environments. So assuming you have the computational resources, you can actually try to create essentially a mini version of the environment in which you are running and share it. The good thing here is that it's self-contained, so you basically don't need to worry about other dependencies to work, and it's also isolated from your machine. So it works both ways here. If I'm receiving something from somebody, sometimes I like it when it's isolated from my main machine, so that if there is a problem, it doesn't kill my entire machine. So that's kind of the advantage of it. But especially if you're working in Python, you're going to have some practice to this because it's a little bit harder in Python to get all the libraries working together and get a proper environment working together. But it works. Multiple virtual environments can coexist on the same machine. And if you're using Anaconda in Python, you're already doing this. Every time you're creating a new Conda environment, you're basically creating a virtual environment that coexists. Actually, hopefully, if you're using Anaconda, you're not using the base to install everything. You actually put it into a different environment. And so when something does happen, you can just destroy it and restart from scratch. So why do we do virtual environment? So a couple of reasons. The one that I already said is it isolates from your machine. And so it actually helps if there is a problem. But most likely it's because it works on your machine and then all of a sudden it doesn't work on other people's machine. So sharing the environment actually helps with that. So it might have to do with incompatibilities. It might have to do with different version installed. Whatever the reason is, it's always good practice to share exactly what the computational environment was. So how you share those environments? So there is environment managers like Anaconda that I'm sure a lot of you are familiar with. Another one is Memba. If you're using pip, there's something called virtual environment that actually allows you to work with this. And essentially it creates like a mini environment for you to put the libraries that you need on your own computer. To share it, you basically can write an environment file. This is what it looks like in Python. And we'll cover this on how to do it and what the best practice are. If you want to look at one, there is one for the PaleoClean paper that is fully pinned in this case because the paper is actually old now. And so we wanted to make sure that it was actually going to run. So that's the minimum you can do, but then people are still responsible for installing that environment on their computer, and things can go very wrong, especially with Python. I don't know if it's the same in R, but creating environments that are shareable with those type of files can actually go very wrong. Another way of doing this is to actually containerize your code using something like Docker. And essentially it creates an image of the infrastructure you have on your computer, the operating system, things like this, and allows you to share your code where you know it's actually going to run. So basically, it includes, it's basically a virtualized computational environment that allows you to run one or multiple software images within it. So now you're not just sharing essentially the libraries, you're actually sharing the entire infrastructure under it. Docker, which is what we're actually going to be talking about in the next couple of weeks, is the one that I use personally the most, but other companies also have different types of containers, but it actually works quite a bit. It's the same way. So why do we want to use containers? It's going to improve reproducibility because now you're running the same application with the same OS, with the same environment, with the same everything. You can encapsulate functionalities and deploy some application. So for example, you have a Windows machine, but the code is in Unix based tool. Then you can actually grab the container, run it within the container on your Windows machines. It helps maintain applications and versions because now the code is already completely encapsulated. So even if things change over time, it's a different version of the libraries and so on and so forth. This is a fixed image. It helps with testing things. If you're providing somebody with the container and the data, they can actually test that everything is working properly. And also it's fairly efficient to actually do it this way. So how do you find existing containers? There is container registries such as Docker Hub and Quay.io. So basically they contain essentially Docker images. So think about Docker Hub as GitHub, but for containers instead of software. And it helps you maintain version and release images through time. So same way as you would release version of your software through time, you can release version of your containers that might contain a different version of the software or a different version of your workflow and so on and so forth. A lot of them integrate with GitHub, and we're actually going to cover this on Thursday on how to write a automated workflow for it to create a container out of the information in your GitHub repository. Not gonna lie, it does require some expertise, especially when you actually get to more complicated things like having R and Python mixed together or having .exe files in there. Things like this can get a little bit more complicated, and actually gets complicated fast, but it's actually very useful to do it. For notebooks, you can actually use something called Binder, where it actually, what it does is that it goes from your GitHub repository directly to an interactive notebook, and we'll show you how to do it on something called My Binder. And so what it does under the hood is that it takes your repository in GitHub, it creates a Docker image under the hood for you, and then serves that Docker image on the cloud for you to be able to actually launch a Jupyter notebook from. And all you have to do at the very basic part to it is give that environment file, put the URL of your GitHub repository in, and launch. That's it. And it allows you to share your workflows. There is one major caveat to this, is every time you click launch, it tries to recreate the Docker container. And so as time passes, it gets harder and harder to create the container properly with the right versions of things. So that's the major caveat to it. But it's one good way to share workflows very quickly with people.
A note for people using R, we can also use My Binder to launch a cloud version of RStudio and interact with your workflow that way.
So how do you cite the workflow in your paper? So your method section in English should still describe your workflow. And you can also include a sketch of that workflow in your paper. So that's where doing the abstract workflow is very useful because it gives an idea of what you've done without going too much into the details. And when you're using basically notebooks to do workflows, follow the same principle as software, quite literally. It's going to be on the GitHub repo. You can get a Zenodo for it. You can get a citation. Everything else is the same, and make sure your version as well. All right, and quickly, I'm going to go through the idea of provenance. Basically, what provenance is explaining to people where things are coming from. So it could be I sign a document, so you know the document comes from me because my signature is on it. It could be a document explaining where things are coming from, or it could actually be a method explaining this is how we took data X, transform it to get data Y. So in terms of pillars of provenance, you need to look at processes, resources, and entities. In terms of processes, it has to do with computation steps and actions. So basically make sure that you document what are the computing steps that you're following, what actions are being done so that actually people can follow what you've done. In terms of resources, has to do with things like documents or data. And in terms of entities, we're talking about people and institution. And all of this combined together to actually tell you where the information that you have come from. So this is why at the beginning I was saying you should get a permanent ID even for yourself, because it allows to attribute essentially the data to you. It's kind of like giving it a signature. So what is provenance exactly? It's basically all the information about the entities, activities, and people involved in producing a piece of data, which can be used to form assessments about its quality, reliability, and trustworthiness. So For instance, which one do you trust the most? An excerpt from the IPCC report or a blog post from an unknown author? And so basically, the basic thing here is that you trust a source versus another source because of its provenance and because you're actually trusting the entity behind it, you're trusting the process behind it, things like this. So in terms of reporting provenance, there exist ways of doing it. And, again, this is where the difference between FAIR and scientific paper of the future comes in. The FAIR is really for everybody in the community to make sure that provenance is tracked. So I'm just going to tell you what you can do to contribute to provenance. So again, provenance means that you share your workflows with as many details as possible so that somebody can follow where things started, what happened to them, and where they went. And you use a unique identifier for your data, your software, your workflow, yourself, your co-author. So if you really want to take it to the extreme step, every single step in your workflow should also have somebody, a name attached to who did what, essentially. So journals will provide a unique identifier for your study. So if you publish in a journal, you're going to get a DOI, right? And the journal paper is going to have your name with your ID attached to it. And if you did your job right, your section should include your data and your workflow, which also have DOIs. And so basically, by using the paper, you can actually link the provenance of where things are if you actually did your job properly. And so your job here is not to do everything yourself, is to just help essentially other entities linking the artifacts to you, the study, to give it essentially that provenance trace and trustworthiness. All right, any questions on what we covered? I know it's a lot.
Yes, I have one question, Deborah. Deborah, at some point we are gonna apply this. For example, I saw you're showing us how to put the height or the configuration of the environment, like Python environment of our project. Are we expected to do something like that, like to create a file like that, like those one?
Yes. So today was just the general presentation of, what are the different pieces and how do they fit together. Tomorrow, we're going to talk about sharing through GitHub first, getting a Zenodo, using GitHub for your research, essentially. On Thursday, we're going to talk about creating those environment files and basically creating Docker containers through GitHub, putting them somewhere so that people can actually reuse it and so on and so forth. So today was the big introduction of why do we do this and what are the different pieces. Tomorrow and Thursday is we're actually going to do the pieces.
Great, thank you.
Any other questions? All right, so let me unshare my screen for a second. There is homework for you. Find the homework. All right, so that's the hands-on part to it for today, which is to get everything ready for you to be able to put it on GitHub, create those environment files, and so on and so forth. So I'm going to put a warning out there, but to actually be doing all of what we've talked about, everything has to be shared publicly. So a lot of things that we've discussed so far, like using GitHub and so on and so forth, there are ways to keep it private until you're ready to publish. But then you can't get a Zenodo, there's a lot of things you cannot do with a private repository. So everything we're doing kind of requires that you can do something publicly. And so we kind of recognize there might be three case scenario that applies to you. The first one, which is the best case, that you're ready with your publication or you've already published your paper and you actually want to put the data and the software that was attached to that publication out there. In this case, great, use this and we'll help you. And we'll help you get all the DOIs and so on and so forth for your publication. The second issue that you might have, the case 2, which is least ideal for this workshop, but we understand that happens all the time, which is you're ready to publish in a few months, but you can't have your data and your results public yet. So here are the way to do it. The first is put everything private. And again, not ideal for this workshop and definitely not what we recommend because you won't be able to get the Zenodo. You won't be able to really participate. So here are the options that you have that we've used before. The first one is withhold the data. So basically nobody can run your workflow and get your data, get your results if they don't have the data to run it. So just don't put the data publicly out there for now with the understanding that you'll do it eventually. So if you have any steps in your notebook that requires downloading data that's not publicly available, things like this, then remove that essentially, like put it blank, leave it blank for now.
Hey,
Yeah.
Deborah, doesn't Zenodo allow for closed as well as embargoed access? Then why can't, I mean, you can't have a private repo, but you can have closed and embargoed data, right?
You can, but the problem is you're going to have issues with the link between a closed repository and Zenodo. Or at least last time
Okay.
I tried to do this, it wasn't working.
Oh, interesting. Okay, cool. Yeah, I've done like closed in the past and it worked, but maybe something has changed. So, okay, I'll try that. Thanks.
I've tried it before and it would not, like, I would have to enter a lot of information manually because it wasn't reading the repository properly.
Oh, I think there's, sorry, I think you're right. So the repository still can be, well, actually, I don't actually know because in the end, it's using a webhook to just move all the data, right? To just create a copy. I guess I don't really know if embargoed access would mean that others will not be able to access it via Zenodo or others won't be able to access it via the repo link. So, okay, cool. I just thought I'll ask because I remember those settings being available on Zenodo. So, yeah.
Yeah, but when you do the link with GitHub, have you ever tried to link through GitHub directly? I'm going to assume no, but
Sorry, what?
so there is a way to link through GitHub directly so that the two are in.
Yes. You switch on those toggle switches and you basically sign in with GitHub and then it uses a webhook that you give permission to. And every time you create a release, it basically creates a release in Zenodo as well.
Yes, and I think some of those functionalities unfortunately requires the repo to be public.
Got it. Okay.
Things might have changed, but last time I checked, it had to be public. So, okay. So one way is to withhold the data so that people can actually reproduce. So withhold the data, withhold the query. The second thing you need to do is in a Jupyter notebook, you can actually clear all the output. So only the cells with the code is going to show, but the output won't show. So people won't be able to see, the figures, won't be able to see anything like this. And people can't run it because you cannot run code without the data. So that's one way to do it. And so when you're ready, then you can actually retoggle essentially the data if you want to think about it this way, and then everything will be ready to go. The last case for this workshop, especially if you're not in case 1 or case 2, is create a short script with pseudo data, something very easy that you can share easily and follow the instruction for case 1. So an example of this is, let's say you're very interested in using somebody else's toolbox. They might have a simple script for you to play with to learn how to use that toolbox. So you can actually do this. It could also be something as simple as opening tabular data into a data frame. At this point in time, it doesn't matter what the notebook look like. It doesn't have to be like the best science available. It just has to have basically some code into it. So if you are not comfortable with case 2 or you don't have a case 1, case 2 scenario, that's the case 3 for you to be able to learn the publishing aspect to it. Okay. So if you're doing case 1 and case 3, publish your data on an appropriate repository for your field. So in case 1, sorry, for your case 1, it should be your field. For case 3, use Figshare so that you actually kind of get some practice on how to share your data as well. So put your data on Figshare and then basically link to that data on your notebook. For case 2, because we won't be able to test anything, make sure your software is running properly with the local data that you have on your computer, and then clear out your outputs. So for the software workflow part to it, in case 1 and 3, make sure that everything is in one place. If you're using scripts instead of a notebook for the workflow, prepare a sketch of your workflow input and output for sharing. So those like sketch that we were showing with the arrows. If you're using a notebook, then make sure that you have some idea, like respecting that, each either each cell or each section is a component of the workflow, and you describe what's going on essentially into it. And I'll show you an example after this. In case 2, and if you have, like, basically you want to clear all of your outputs so that nobody can see what the results are. In a notebook, if you go to edit, do clear all outputs, and it will only show the code without showing any of the figures or any of the things that would print out essentially. And again, make sure you withhold the data. So cut out the cell with the data. And if you're using R Markdown, what you do is do results hide before you share. And then prepare a README file. So if you used GitHub before, you know what they look like. But essentially, write text in Markdown that describe the study, the data, the software, and the workflow that you're using. And I'll share those slides with you. Am I actually sharing my screen?
Yeah, you are.
Putting this in the chat. But these are good examples of READMEs that actually describe the workflows in different ways. So if you want some inspiration, that's one way to do it. So again, today you're in the, I need to write basically what's called documentation for what I've done phase of this. And then tomorrow and Thursday, we'll talk about putting it on GitHub, getting DOIs, sharing your resources, and then on Thursday, making Docker containers and my binder links. All right, case 3 people. This is the example that I'm going to use tomorrow to show you how to do things. And you'll see how simple you can make it. Wow. So if you're not familiar with it, if you want to share the content of a notebook, without sharing all the computational environment and so on and so forth. GitHub used to render them, now they don't, but you have something called nbviewer.org. You give the link to the Jupyter notebook, and it will render a static version of it for people to be able to see it. They just can't run it unless it has a MyBinder environment. But basically, this is how simple, like data, visualization. And that's where I left it. So it can be that simple of like 3-4 lines of code, just to show how to do something essentially. So I think it took me like 10 minutes to create this.
This is only possible because you didn't clear the outputs, right?
Yeah.
Okay. So if you cleared the outputs, then this website won't render them, right?
Well, it will render without the output.
Exactly. Okay. Just making sure because
So,
you
yeah.
mentioned initially to clear the outputs, and I was just making sure that in
Sorry.
this scenario that won't work.
This is for case 3. So case
Okay.
1 and case 3 do not clear the output. So if you're ready to share, or if it's something that you don't mind having public, don't clear the output, leave it. Case 2, if you're clearing the output, it will still render, it just won't render things like this. Or it won't render the visualization. Does that make sense?
Yep.
But it will still show you the notebook, the code. The code and the text that is not the executed part. How is that? Does that sound good for everybody?
Mm-hmm.
Yep.
Okay, just show of hand, who would be in the case 1 scenario? You're like ready completely to publish. 1, 2. Okay, who is going to be in the case 3 scenario where you're going to have to create a very small example to do something? 1. Okay, so that leaves 2 of you in case 2. Sam and Turi.
Sorry, I was going to raise for one. I was looking for the raise hand option.
No worries. Okay, so we don't actually. And Turi, you're in case 2, right?
Yeah, sorry. Yeah. Case 2.
Case 2. Okay. So, are you using Python or R?
R.
Okay, so I think just make sure that you basically use this command so that it doesn't return the output.
Sure.
Okay, second show of hands for tomorrow and Thursday. How many of you are going to do Python? Just raise your hand for Python. 2, 3. Okay, so half and half, almost. Okay, so things are going to be a little bit different between Python and R. So what we're going to do is, if you're doing Python tomorrow with me, we'll meet on the Zoom of today. For people doing R, Dave will provide a different link in Slack so that you can meet with him, because things are a little bit different between the two when it gets down to the details. So it'll be easier to have the examples in both languages. If you're doing something, if you're doing Julia, come to the Python part to it. If you're doing MATLAB, go to the R part to it. It's closer. Sounds good? Okay, and Alfonso and Sam, because you brought that up, are you going to need a lot of computing resources to reproduce your workflows? What do you have? No? Okay. Do you need GPUs or CPUs only?
I think CPUs are fine, and I think
Yeah.
Colab does give you a single TPU if you needed it. So you can technically get a GPU if you wanted it.
Yeah, it's just for my binder, because we're gonna show you how to share through my binder, not just collab. If you need a GPU, there is a little bit of additional steps. So let me know if you want to cover this or if we just need to cover CPUs.
Got it. Okay. Is there a is there a recommendation as to like one better than the other? Kind of like, is Colab better than Binder for certain use cases, and why you would recommend one over the other? I'm just curious.
So they're not exactly the same. So collab basically is really meant for collaboration among different people, right? And it's basically a Jupyter hub that's maintained by Google. And so they have pre-installed libraries in there. So if you're using those pre-installed libraries, fantastic. If your library can be installed through pip, also fantastic, because you can just do that command line installs for a notebook. If you're requiring things like Anaconda or things like this, then it doesn't work anymore. So that's the Google Colab part to it. What Binder, my Binder, and basically the underlying Docker does is that it really reproduces your computational environment. So basically you can install the libraries that you need, how you need them, with the proper versions that you are using, and so on and so forth. And so for posterity, like if you're actually just saying, I'm done with my study, 6 years from now, your Docker container should be working. However, 6 years from now, you might not be able to rerun the same code on Google Colab because Colab would have evolved. The drawback of Binder, my Binder and Docker, so obviously harder to use a little bit, like on your side, there is a little bit more work involved. The other drawback is it's not collaborative in nature. Like you can't all go into the same image at the same time and, change the notebook. You would have to use GitHub essentially to change the notebook in GitHub and then recreate the Docker container if you wanted to do it this way, probably not the best way. And also it can be very slow to get a binder repository built, especially if you have big libraries. And by slow, I mean it could take 15, 20 minutes just to get the thing set up. And also, you're not saving anything in my binder. It's temporary. So basically, you run it, you play with it, and then once you close your browser window, that's it. There is no, unless you download the notebook on your local computer, there is no saving. Google Colab allows you to keep the notebook essentially in your Google Drive with the changes and so on and so forth. So they're really meant for different things.
Got it. Okay. So Binder will give you elevated access. Like you can use sudo in Binder.
You can, yes, for a Docker file.
Okay. Interesting.
So
Thank you.
Binder essentially, I should say my Binder, but Binder in general, what it does is it creates a Docker container, so you can do whatever you want to within that container using a Docker file. And you have pretty much access to everything that you need, whereas Google Colab is basically a Jupyter Hub.
Got it.
And I'm not even sure Google Colab works in R.
It does.
It does? Okay.
Yeah.
Haven't done R in a very long time.
No, you can change kernels. You can do it R. You can even do JavaScript, Ruby on Rails if you wanted to.
But you're still stuck with the Jupyter interface, right?
Yeah, you can technically get to the terminal if you really want to do that, because you are getting, like, once you connect a runtime, you're effectively getting compute that's allocated to you using a shared VM, right? So the difference there is that it's a preemptible VM. If you're not using it for some certain time, you get disconnected from the runtime instance. But you could theoretically do certain things the same way in which you can do it in a normal machine. I don't know if you could actually get to like your command window the same way in which you might be able to get in your binder environment. So that's the only difference, but effectively everything else remains the same. You have the same instance, and theoretically you can do certain things apart from, I believe, sudo, which I don't think either Docker can do either, because sudo will allow you to gain privileged access to their backend system, which they want to avoid at any cost. Or actually, Docker does allow that. That is a security risk in its own way.
Docker would allow you to do it in the Docker image, not in the machine on which it's running.
Yeah, but there's a whole reason in scientific studies, while they moved to like a lot of science in HPCs use Singularity now rather than using Docker, because of the fact that Docker will allow you to gain elevated access to the backend system and to do some nefarious things that you shouldn't be able to do. So, yeah.
Yeah, well, so yeah, I'm assuming a lot of scientists are not going to go and do the nefarious things, so Docker should work. Any other questions? And nobody here is doing Python and R marriage, or Python and MATLAB, or in MATLAB.
The manual workflow I have, but I'm willing to do a quick Google search on just making the figures from the output files in R to make life easier.
Yeah, I mean, you should be able to do everything in the Jupyter notebook. I've done this before, where you can basically use magic so that you run the R stuff in the magic and then use the notebook for the visualization. That's one possibility for you as well. But we would have to have a look at your notebook to see how involved the R code is.
Mhm.
Have you ever used magics before?
No, I haven't tried combining the two. So I'm gonna focus the goal on me getting the something like a container working just for R.
Okay.
Yeah.
All right, so we'll see you tomorrow at 9 synchronous. And again, Python, same Zoom, or other Zoom. And if you have questions this afternoon on how to prepare your stuff and so on and so forth, ping us on Slack and we'll come and help you.
And these assignment slides are available online.
I think
They're in the chat, right?
I put them in the chat, yeah.
Oh, okay. Gotcha. Thank you.
Okay, see you tomorrow.
See you tomorrow.
Thank you.
Bye.